A very good day, everyone. Welcome to the tutorial on theory and practice of voice conversion. Together with me today, we have Berrak Sisman, Tsao, and I'm Haizhou from National University of Singapore. And three of us will deliver this tutorial in the next roughly 3 hours, including the breaks. So I'll be the first presenter and followed up by Berrak and Yu jointly for the rest of the session. This tutorial covers several topics. The first one is on introduction, history, and applications. I'll cover this too. And then Berrak and Yu will cover the rest of the topic jointly. Well, I was very much looking forward to meet all of you in New Zealand, but due to COVID-19, we now have to do it online. I hope that the online presentation will be just as effective as in-person presentation. And this tutorial is built on top of a recently published paper on an overview of voice conversion and its challenges, from statistical modeling to deep learning, which is in IEEE ACM transactions on audio, speech, and language processing. You can visit the website if you are interested in knowing more about the contents of some particular discussions. You can visit the IEEE website, IEEE Explore website, and this paper is for open access. So first of all, let's talk about what is voice conversion. Voice conversion originated from, our human art of voice impersonation. We know that in stand-up drama or in movies, you have seen people impersonate another person's voice. And we want to do that in voice conversion, but with computer. That means we want to automate the process by using computer algorithms. So in the picture, you can see that you have a person, you have a boy, which is referred to as a source speaker, and we want to convert his voice to the girl's voice, the target speaker, okay? And maintaining the language context. That means we want to carry the words that the boy says over, but present it as if the girl is talking. Of course, there are other aspects of voice conversions as well. For example, we want to convert one voice, happy voice, to a sad voice of the same speaker. Previous slide I talked about converting the voice from one speaker to another. And in this one, we say that we want to convert the voice of the same person from one mood to another, happy voice to the sad voice. So in this particular study, we may want to model the differences between the different emotional expressions. The research also was extended to other topics, as assistance for voice generation. So for example, if people who has a problem vocalizing the voice, for example, there's an injury in the larynx, then there's some device that is called electrolarynx to help vocalize the sound. But it is not very clear and people do not use to it. So how to convert such voice into clear voice that we can hear? And there are also other sounds. For example, whisper is another way of speaking, but the voicing is greatly limited. And how to convert whisper voice into clear voice. Dysarthria voice, that means people who have speaking impairment. and they don't speak clearly. And how do we convert their voice to clear voice? All these share the same technology, same voice conversion technologies that we develop, the same theories, and these are just representing different type of applications. So in terms of applications, there are many more areas. You know, the research of voice conversion will focus on like two aspects. One is on the theories, the algorithm, the techniques, and all. Another one is trying to bring the theory into practice, into applications that we will talk about in today's tutorial. Here, I will just give some examples. So for example, by changing, just now I mentioned that by changing the emotion, you can make a happy voice become a sad voice. But if you do it properly, you can also convert a reading voice. For example, here I play the sound.
Twinkle, twinkle, little star, how I wonder what you are.
By using the melody as a reference. You can convert the reading voice into a singing vocal.
Twinkle, twinkle, little star, how I wonder what you are.
So you can see that this synthesized voice is rather natural, but it was generated from the reading speech by changing the prosody. There are many other aspects of voice conversion uh, that you can find in the literature. They are designed for different type of applications. For example, to personalize uh, text-to-speech synthesis. It is also by taking text as input, but generate a personalized voice. Dubbing of movie and games. You can project a sound for particular cartoon characters on the movie, and you can convert the emotions from one another, of either from the same speaker or from different speakers, or from one speaker to another. And voice conversion techniques is also studied together with speaker verifications, because today's voice praying speaker recognition has been used in many commercial applications. And there's a concern that advancement of voice conversion techniques may uh, uh, provides tools for the adversaries to attack the systems. So how to study to study how the speaker verification system interact with voice conversion system, it will be an interesting topic as well. So that's also part of the voice conversion studies. To understand the theory of voice conversion, I think we need to start from understanding the differences between the speakers. In this slide, you will see two voices, different illustrations from different perspectives of two voices of the same content by two different speakers. So on the left-hand side, on the left left column, you see uh, the waveform on top A, and then you see the spectrogram B, and then you also see the C is the Foreman trajectory. You know, Foreman represent the energy concentration of in the spectrum for the speech, and you see the different trajectory between two speakers. D is the pitch contour, the fundamental frequencies. You can see the fundamental frequencies can be 0 when it is for the unvoiced sections. For voice section, usually has a value between 50 to like 200, for example. Okay. And then the last one, E, is a plot of the energy envelope. Okay, so you can see from different angles to see the same speech waveform. And if you see the left column and the right column, by comparing them, you will see that although the speech contents is the same, but the plotting, the diagrams are very different. Okay, that shows there's a great variation between speakers. From a speech perception point of view, a speech can be represented in three main elements. So you have a speech in the center, and then you can see that there are three main elements. One is the content that the speaker want to say, the words, the lexical content. And then on the top, you see the prosody. The prosody represents the duration, the energy, the pitch trajectory. That is basically to render the emotion of the speaker. And the third element is the timbre. The timbre, we can also call it, is the voice print of the person. So a person has a unique voice print, has a unique timbre. So we have the three elements. Well, in different books, they talk about speech in different elements of speech. But in this particular context of voice conversion, we are particularly interested in these three things: the content, the prosody, and the timbre. And in voice conversion, we would like to fix the content. We want to fix the linguistic content. And we want to, by changing the prosody, we can change the emotional expression, the mood of the happy sound to sad sound, to reading speech, to singing speech, singing vocals. And by changing the timbre, this is the focus of most of the studies. By changing the timbre, we change the voice from one speaker to another. I would like to hear next. I would like to show you a demonstration, and this is actually a demonstration that was presented quite long ago, 2006, and I got this demo from my friends, Professor Kawahara. I will stop sharing this. I will share my another screen. So as you can see that in this web application, you can see a triangle, and there are three corners of the triangle that represent three types of mode. So one is angry, well, it's written in kanji, and then another one, and another angle is written in kanji as happy, and then another angle is sad. Okay, so you have three angles, and then actually by changing the parameters of the voice, you can change the mode of the expression. Let me start with the happy sound.
I love you.
And the angry sound.
I love you.
And the sad sound.
I love you.
Then you can actually interpolate.
I love you. 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 I love you.
So this demonstration, just trying to share with you, through this demonstration, I want to share with you the idea that by changing the parameters in the speech analysis, you can actually control different elements of speech. Let me stop this sharing and go back to the previous slide. Okay. So when we talk about speech voice conversion, I would like to also introduce a concept that is called vocoder. This was a study long ago at the beginning for speech communication. You know that when two persons are face to face, then you just talk, the voice will be transmitted over the air, right? And acoustically. But if two persons are not in the same place, then what do? You make a telephone call. And to make a telephone call, basically, your speech is analyzed, encoded, and transmitted over the air, and then received on the other end and resynthesized back to the signal. And this was basically the traditional way of voice communication. And the encoding allows the audio signal to be compressed, to be multiplexed, and to be encrypted during the transmission. And the study shows that actually, since we're able to analyze the speech into parameters, and we are able to manipulate the parameters to change the properties of the speech and resynthesize it. And this provides a tool for voice conversion. So the vocoder actually has two parts. The one is analysis, to analyze the speech waveform into parameters. And the second part is to reconstruct the speech from the parameters. And the particular part that was the green section in this slide, feature conversion, represents the research focus of voice conversion for many years. So we are trying to find a mapping function f that map input x into output y. And making use of the vocoder mechanism, we're able to reconstruct a target voice, which sounds slightly different from the source, as if it is spoken by a different person. Right? So this vocoder techniques, when you read voice conversion literature, you oftentimes encounter the discussion of vocoder, because vocoder provides the tools, the platform that allows us to do voice conversion. Is particularly in the older literatures. A vocoder is an important part of the voice conversion study. And today in deep neural network approach, a vocoder continue to play a role. But please remember that vocoder is not part of, it is not doing voice conversion itself. Vocoder is a technique that was used for speech generation, for communication, but we adopt vocoder as a platform for voice conversion study. So if you want to know particular which part of the in this graph is doing the voice conversion, that is the center part, the green box feature conversion. Okay, and the vocoder actually refers to the analysis and the synthesis part of this pipeline. Over the years, speech synthesis or text-to-speech synthesis technique has made a lot of progress. And the study of voice conversion actually leverage on the progress of speech synthesis, because both of them share many common tools and common goals. For example, both of them want to generate natural sounding speech. So you need a speech generator, you need a good vocoder, for example. So the studies of speech synthesis, many of the techniques in speech synthesis are adopted for voice conversion. Here is this slide kind of give a summary of the research progress in speech synthesis over the years, from the 50s to the most recent one that I don't get the most recent sound, but this voice in 2013 from my lab as represent one of the recent progress. Let me play the sound from 1959 from Haskins laboratory.
I printed this file without looking at a spectrogram. Can you understand it?
Can you understand it? So this is a sound that sounds very robotic. It was actually recognized as the first automatic reader of spectrograms into natural speech. And that explains why now in movies, if you see robot a robot is talking, robot always sounds like this. It's because this was the sound, the signature sounds of huskies. And over the years, speech synthesis has made a lot of progress. In today's speech synthesis, basically you cannot easily tell the differences between the synthetic voice versus a natural human voice. Let me play a sample to give you a flavor of it.
Something at a medium price near the shopping center.
It's in English, it's in Chinese.
依然是困扰我们的尴尬之一。
And remember, this was a sound, a slice, there was a sound clip that was 7 years ago. In the recent years, there are even more progress in speech synthesis that render very natural sounds. And all these techniques can be used for speech generation of voice conversion. The studies of voice conversion started a little bit later than speech synthesis. The earliest literature was from the 80s. At the beginning, people tried to build the mapping functions. Remember the mapping function that I showed you in the slide of vocoder, right? So at the beginning, we try to build functions using non-parametric techniques like vector quantization. Later on, we realized that actually it is important to convert the specific properties of speech that represent speaker characteristics from one another. Therefore, we build models to address those issues. For example, we built frequency warping methods to map the format. And we also realized that parametric techniques kind of always give an average voice, which lacks a variance. So we built better models such as DKP-LS with kernel function to model the conversion. And this represents the second stage of modeling in the voice conversion studies, with the highlight that we has gained a better understanding of what to make a good voice conversion. And we try to build those constraints into, or to focus on those speaker characteristics, to reflect the modeling of the speaker characteristics into the modeling. So that represent the second stage of research between the 80s and until early until 2010, around that time, when we transit from statistical method to neural approaches. And the recent progress in deep learning provides us a lot of tools. For example, all kinds of neural networks, deep convolutional neural network, recurrent neural network, the GAN frameworks, that provide us many tools to do to perform voice conversion. In the past 40 years, we are always struggling with one limitation, which is limited data, limited training data. You know, when we want to build a voice conversion system, ideally you can have the voice samples from two speakers, right? From speaker A and speaker B, and ideally the speech corpus are in parallel. That means they speak the same content, so you can easily derive the mappings between speakers for each particular sound. But this is not practical because it is not always possible to record parallel corpus and in large volume. So for the techniques since the 80s to the beginning of the non-parametric technique to the later on the parametric technique of the statistical approach, we always try to make good use, invent a technique to make good use of the limited training data. And the progress basically the better study always show that, you know, with limited training data, better algorithm provide a better mapping, so it gives better results. But when the neural approach to voice conversion comes, it opens up a new door towards this research. Basically, with the deep learning techniques, it allows us to leverage on a greater volume of databases from multiple speakers. So for example, you can think that if you want to build a voice conversion, how to generate the voice, the vocoder, can be actually trained from large publicly available multi-speaker corpus. We don't need to build a voice generator for each of the voice conversion system, right? So in this way, the things that are common across speakers can be learned by the deep neural network from large database. And the research can just focus on how to convert the differences between the speakers. And this is the particular things that deep neural networks as a tool provides us the new way to address voice conversion problem.
Thank you, Professor Lee and Berrak. Hello, audience. I'm Tsao from Academia Sinica. I'm going to take over the presentation from now. In the following, I will first present the parallel data for voice conversion. In this topic, we will first introduce the main concept. Then we will introduce some traditional approaches. Finally, we will introduce some deep learning-based approaches. Each human has a unique speech generation structure. The structure can be formed by several parts, such as lung, vocal cord, nasal cavity, and tongue. Through education, we are learning to pronounce the same content in the same way. For example, two speakers pronounce the same sentence. We can clearly know that the utterances are from two different speakers, and we can understand that they are speaking the same content. When we try to convert speech from one speaker to another speaker, we actually intend to only convert speaker information while maintaining the speech content. Generally, we can analyze speech signals and the corresponding acoustic features in segment-wise and utterance-wise. The segment-wise speech signals or acoustic features convey the speech content, and the utterance-wise speech signals or acoustic features convey speaker or emotion information. When training the voice conversion systems using speech with fixed speech content, we call it parallel voice conversion. Since the speech content is fixed, we only need to convert speaker information. Ideally, we can have paired source and target waveforms, and thus paired source and target acoustic features to perform parallel voice conversion. Then we can use a set of training data to estimate a transformation that can perform frame-by-frame mapping. That maps the source to target acoustic features. The main concept is that since the content is the same, by converting acoustic features, we actually convert speaker information. However, although speech content is the same, the overall length of source and target speech signals may be different. This is because the speaking rates and the speaking characteristics of these two speakers may be different. For example, the source speaker may use 3 frames, say 90 milliseconds, to pronounce the word she, while the target speaker may use 2 frames, say 60 milliseconds, to speak the same word. Therefore, although paired speech signals are prepared, we could not directly compute the transformation for the frame-by-frame mapping. To address this issue, we generally perform a dynamic time warping to align the source and target acoustic features. With the aligned source and target acoustic features, we can then estimate a transformation. This transformation characterizes the mapping from source to target acoustic features. During conversion, the source acoustic features are treated as input to the transformation, and the converted output is the target acoustic features. Many models have been used to form the transformation, including Gaussian mixture models, exemplar-based models, and deep learning-based models. In the following slides, we will review some of these models. The Gaussian mixture model is a very well-known model for parallel voice conversion. With the aligned source and target acoustic features, we first form joint vectors by concatenating the source and target features. During training, we estimate a GMM model based on the joint vectors. When performing conversion, given the source acoustic features and the trained GMM model, we can use MMSE to obtain converted features. In addition to MMSE, the MLPG algorithm can also be used to convert source features to target ones with considering parameter trajectory information. Another type of approaches is based on dictionary learning. The idea is to prepare paired dictionaries. That is to say, one dictionary for the source speaker and the other dictionary for the target speaker. We represent these two dictionaries as AS and AT in this plot. Each dictionary consists of a set of acoustic templates. Usually, we can use a batch of acoustic features for the template or a single acoustic feature to represent the acoustic template. Because the dictionaries are paired, the acoustic templates in these two dictionaries are also paired. More specifically, since the speech content is the same, the only difference of these templates in these two dictionaries is caused by speaker information. In this IEEE TASLP paper, the author proposed to use exemplar non-native matrix vectorization approach called ENMF. In this approach, we directly collect speech templates based on the training data. When performing conversion, given source speech, we first estimate a weighting matrix W. This weighting matrix W describes how to reconstruct the input speech by linear combinations of the dictionary. Because the dictionaries are paired, we can use the estimated weighting matrix W and the dictionary of the target speaker to generate the target speech. Since the speech signals are paired, we consider that the weighting matrix W models the speech content, Accordingly, by changing the templates in the dictionaries, we can actually changing the speaker characteristics. In this ENNF voice conversion paper, the speech signals are treated as templates and saved in the dictionary directly without further processing. It is clear that when we have a lot of training data, the size of dictionaries can be very huge. This will increase the online computation cost to compute the weighting matrix W. To address this issue, two directions of approaches have been proposed. The first approach is that since the dictionaries are paired, we can concatenate them into a larger dictionary. Then some clustering approaches can be applied to the concatenated dictionary. In this way, similar templates can be merged, and thus the dimensionality of these two dictionaries can be reduced. During conversion, we use the dictionaries with reduced dimensionalities, AS prime and AT prime in this plot, as the source and target dictionaries respectively. Then we can estimate a weighting matrix W. Based on this weighting matrix W, we then generate the acoustic feature for the target speaker based on the AT prime dictionary. This approach is called Joint Dictionary Learning, NMF, the JD-NMF approach. We propose to apply the JD-NMF to improve the intelligibility of impaired speech. We aim to apply the JD-NMF to assist individuals who receive oral cancer surgeries. The oral cancer is one of the top 5 cancers for males in Taiwan. These are the photos of individuals before and after receiving oral surgeries. It is clear that after oral surgeries, some muscles or nerves may be hurt. Accordingly, the surgery will affect the pronunciation, and thus the generated speech will have lower intelligibility. Our intention is to convert the speech signals after oral surgery to the enhanced one with improved speech intelligibility. In this slide, we show the conversion process and the learned basis in the two dictionaries of the impaired speech conversion. In the top panel, we have impaired speech, and we have a dictionary learned after surgery. We estimate a weighting matrix W, and by copying this weighting matrix W with the dictionary learned from before surgery speech, then we can obtain the converted speech with higher speech intelligibility. In the bottom, we present the dictionaries learned from speech after surgery and before surgery. Each basis in the dictionary represents a particular phonetic or acoustic template. For example, this one only covers the low frequency part. We believe this basis represents a vowel sound. And this one has high frequency part, and we believe this one can be a consonant sound. When we compare the dictionaries after surgery and before surgery, we can see the difference is very clear. For the basis learned from before surgery, each basis is very clear. However, the basis learned from after surgery, every basis has some noise components, especially in the middle frequency region. Therefore, we can easily tell that the speech intelligibility using this dictionary should be very poor as compared to using this dictionary. Here are some demos. Top ones are after surgery. Bottom ones are processed by JD-NMF. We can clearly see the speech structures become clear after voice conversion. We also test the STOI scores. The results show that the STOI scores are increased after voice conversion. If you want to know more, please refer to our paper, which is published in APSIPA TBME in 2017. The second approach is based on the locally linear embedding, the LLE algorithm. We first prepare paired source and target dictionaries. During conversion, for each input feature from the source speaker, we select a set of templates from the source speaker dictionary. This set of templates form a smaller dictionary with reduced dimensionality. Based on the sequence of acoustic features, we can obtain a source dictionary set. Based on this source dictionary set, we can identify the corresponding target dictionary set. Then we estimate a set of weighting vectors with the aim to reconstruct the source acoustic features. Finally, with the target dictionary set and the estimated weighting vectors, we can obtain the converted acoustic features. In addition to the GMM and dictionary learning-based approaches, recently several approaches that are based on the deep learning algorithms have also been proposed. Different from the dictionary learning-based approaches, the deep learning-based approaches generally use a mapping function that aims to directly convert the source acoustic features to the target acoustic features. When we train the deep learning models, we generally use the difference of the converted acoustic features and the acoustic features from the target speaker to form the objective function. The most popular objective function is the L2 norm, or the mean square error criterion. To attain better conversion results, some other objective functions have been proposed, such as MLPG, maximum likelihood parameter generation, MGE, minimum generation error, or SCEM, sequence error minimization. Actually, the implementation of the deep learning-based voice conversion approaches with paired training data is very similar to that of the GMM and the dictionary learning-based voice conversion approaches. With the paired source and target acoustic features, the deep learning models are trained to map the source to target acoustic features. To this end, we can use feed-forward neural network model, recurrent neural network model, and transformer-based models to form the transformation model for the source to target mapping. In addition to the dynamic time warping for acoustic feature alignment, we can also use the attention model. In this ICASP 2019 paper, the acoustic features are first encoded to latent representations. The alignment is carried out in the latent space. This matrix shows an example of the alignment result. For this matrix, the x-axis shows the target latent representations, and the y-axis shows the source latent representations. The light line in the middle shows the high attention part. We can notice that the attention matrix actually indicates the correlation between source and target acoustic features. As we know that lighter colors indicate higher correlations in this matrix. With the alignment information from this matrix and the latent representations, we then estimate a decoder that aims to transform latent representation R in this plot to the target acoustic feature XT in this figure. The authors have proposed two approaches to further improve the overall conversion performance. The first one is the guided attention loss. This loss will encourage the attention matrix to be as diagonal as possible. The second one is context preservation loss, which encourages the reconstructed speech to maintain the context information. Next, we are going to present approaches that do not require parallel training data. Since the paired source and target speech signals are not required, as compared to previous approaches, the following approaches have higher flexibility and better applicability. We will introduce the following four parts. First, non-parallel data of paired speaker. Second, disentanglement approaches. Third, leveraging TTS systems. And fourth, leveraging ASR systems. First, I will present the non-parallel data voice conversion. Two representative approaches are cycle-gain voice conversion and star-gain voice conversion. In cycle-gain voice conversion, there are two models, G and D, used to perform mapping from source to target acoustic features. The model in this plot, G S to T, converts the source acoustic features to the target ones. However, since we don't have paired training data, our goal is to make the converted features to have a similar distribution to the target speaker. This is done by DT in this plot. Let us take a closer look at DT. DT is to model the distribution of the target speaker. cycle-gain uses this model DT to identify whether the input speech belongs to the domain T or not. Please note that DT is trained using many utterances from the target speaker, and therefore the speech contents are averaged out, and thus it only models the speaker information. Based on DT, cycle-gain forces G, S to T to generate converted speech signals to have a similar distribution to the target speech signals. Similarly, cycle-gain adopts another discriminator, DS, to model the distribution of the source speaker. Based on DS, cycle-gain forces G, T to S to generate converted speech signals to have a similar distribution to the source speech signals. It is clear, if we only focus on the speaker information, the speech content may be lost. To maintain the speech content, cycle-gain adopts another loss, the cycle consistency loss. That is to say, we have another model, GT2S, in this plot that transforms the converted target speech to obtain the converted source speech. And then we aim to have the original source and the converted source acoustic features to be as close as possible. We denote this loss using the red line in this figure. In summary, in cycle-gain voice conversion, we can convert speaker information by D, and maintain the speech content by the cycle consistency loss. This is the complete architecture of the cycle gain voice conversion. For the top part, G(S)to(T) converts source speech to target speech. Then another G(T)to(S) converts the converted target speech back to the source speech. Our goal is to minimize the difference of the original source speech and the converted source speech as indicated the red line on the top. And a DT is used here to make the converted speech to be more natural and more similar to the target speech. In the bottom part, a G(T)to(S) is used to convert the target speech to the source speech. And another G(S)to(T) is used to convert the source speech to the target speech. We have another cycle consistency loss on the bottom. And there's another DS, which tries to make the converted speech to be more natural and similar to the source speech. The four models, G(S)to(T), G(T)to(S), DS, and the DT are trained jointly. One limitation of the cycle gain voice conversion is that it only supports one-to-one voice conversion. Another voice conversion model, StarGain, is proposed to overcome this limitation. The system is similar to cycle gain and consists of three models: generator G, discriminator DIS, and the classifier C. During training, in addition to acoustic features, a speaker identity vector is also provided into the model G. The model G aims to convert the input acoustic features along with the speaker identity vector to generate the converted ones. The model DIS determines whether the generated acoustic features to have the same distribution to the target speech features. The model C aims to encourage G to generate data to be more similar to the target speaker, so that the classification result will be the target speaker. Then we can perform speaker conversion by changing the speaker identity vector. By converting the converted features Z in this figure, along with the new speaker identity C', we intend to obtain the original speech features, with the aim to minimize the difference of this and this. We can maintain the speech content. Based on this architecture, we can perform many-to-many voice conversion. In conclusion, we try to maintain the content information by part 1, and we try to change speaker information by part 2. In addition to cyclegain VC and StarGain VC, there is another class of approaches that aim to perform non-parallel voice conversion. We can characterize them as the disentanglement approaches. In the following, we are going to present some representative approaches. The first approach is the VAVC. In the VAVC system, we place the acoustic features from the same speaker in both input and the output sides of the model. The goal of the deep learning model is to reconstruct the original acoustic features. In the middle of this model, we intend to disentangle the latent representations into two parts, one for content, and the other one is for speaker information. Every acoustic feature is represented by one content code, and the whole utterance shares one speaker code. The speaker code can be represented by this one hot vector. Based on this setup, the encoder here learns to eliminate speaker-dependent information from the input, and thus making the latent code to be speaker-independent. By adding the speaker code here, we can reconstruct the acoustic features from the same speaker. And similarly, we can train the model using another speaker with another speaker code. When we implement the system, each acoustic feature has its content code. And for the speaker code, we copy the same speaker code throughout the whole utterance. For simplicity, in this presentation, we will present the system in this format: one speaker code and a sequence of content code. During conversion, since the encoder here generates the disentangled content code, by inputting the target speaker code, we can generate the acoustic features for the target speaker. The same idea has been used to disentangle different components in the latent representations. For example, some works propose to disentangle the F0 information, as we all know that the F0 information is very important information to speech in motion. Another work tries to disentangle speech exit. In this presentation, we focus on the content and speaker disentanglement. And the first paper, APSIPA 2016 paper, is actually the first work that applies the disentanglement concept for the voice conversion task. In addition to one-hot representation, the speaker code can also be obtained by a speaker encoder model. In this way, the speaker identity is embedded into a vector where each coefficient in this speaker code vector is a continuous value rather than a binary value. And similarly, we can input the speaker code, which is generated by the speaker encoder model, into the conversion system to obtain the converted speech features. As you can see, we force the encoder to generate content information where the speaker information is removed. During conversion, the speaker code is added back to the system. This is the main concept of the disentanglement approaches. In this Interspeech 2017 paper, the authors proposed the VA-WGAN voice conversion. The main concept is to attain more nature and better similarity acoustic features. We can place a discriminator at the output here. The goal of this discriminator is to force the generated speech to have the same distribution to the target speech, and thus to have the same naturalness and similarity to the target speech. Another way to further improve the disentanglement approach is the multitask learning criteria. In this IEEE TE-TCI paper, the authors adopted two acoustic features, SP and MCC. SP is spectrum feature, which is lower feature and has a higher resolution. And another feature, MCC, is male capture coefficient, which has a lower resolution and is designed based on human perception. From the experimental results in this paper, The author found that by using the multitask learning, the disentanglement can be done better, and we can also obtain improved converted speech signals. In this multitask learning framework, the authors also adopt discriminators for both SP and MCC features. This discriminator aims to force the overall model to generate SP and MCC features that matches the true target SP and MCC features. In addition to place the discriminator at the output, another extension is to incorporate a classifier at the output. The goal of this classifier is to determine whether the speech can be recognized as the correct speaker identity. Therefore, the classifier will encourage this model to generate speech signals with rich speaker information. Another extension is proposed in Interspeech 2018. This is the two-stage approach called multi-target VC. In the training stage 1, this multi-target VC adopts an additional classifier right after the encoder. This classifier can encourage the encoder to more effectively disentangle the content and speaker information. By assigning the speaker code, we can obtain the acoustic features from the corresponding speakers. In the training stage 2, another discriminator and classifier are placed at the output to encourage the decoder to generate better output with higher naturalness and better similarity. In addition, a patcher is used to further improve the conversion performance. During conversion, with the trained model, the target speaker identity is used and input to the decoder system. Finally, we can obtain the converted features for the target speaker. Different from using a speaker code for disentanglement, another way is to directly subtract the speaker information from the encoded representations. In the decoder, the speaker information is then added back, and finally, we can reconstruct the original acoustic features in this way. More exactly, during training, we try to normalize the latent representations by removing the mean and dividing the standard deviation. Since speaker information is utterance-wise, we assume that by normalizing the latent representations, we can remove the speaker information. Then, during conversion, by estimating the statistics of the target speaker using a small amount of training data, the normalized representations can be adjusted. Finally, we can obtain the converted acoustic features. When we implement deep learning systems, such as voice conversion, the model size and online inference efficiency are two important factors. Previously, a mixture of experts, the MOE architecture, has been proposed to increase the online computation efficiency. The overall mixture of expert architecture consists of two parts. The first part is the main neural network model, which aims to deal with the main task. The task can be classification or regression. The second part is an embedding network, which assigns weights to feature maps in the main model. In this way, the overall mixture of expert architecture forms an ensemble framework, and this ensemble framework is proven to have better generalization to new testing conditions. Based on the mixture of expert architecture, if we further assign sparse constraints, some weights are forced to be 0. And for the feature maps to be assigned with 0 values like this and this and this, we do not need to compute them. Accordingly, the online computational cost can be reduced. In ISCSLP 2021, the mixture of expert architecture with sparse constraint is incorporated with the voice conversion task. The proposed method is called MOEVC. In this MOEVC system, the mixture of expert architecture with sparse constraint is applied in both encoder and decoder to increase the overall online computational efficiency. From the experimental results in the paper, we know that when we use this MOEVC, we can effectively reduce 70% flops, floating point operations per second, without noticeable quality drops. Like most deep learning models, we aim to determine an optimal architecture that can strike a good balance between inference efficiency and achievable performance. That is to say, we want to determine an optimal model architecture which has increased efficiency while maintaining acceptable performance. For voice conversion, the main goal is to generate speech with good quality and similarity. Therefore, if we want to determine the optimal model, we should conduct many times of listening tests so that we can determine the optimal model design. Clearly, it is very expensive to conduct listening tests many times. Therefore, we decide to use MOSNet, the MOSNet, to determine the optimal model architecture. We will explain this MOSNet in more details later on. And we will also explain how to use this MOSNet to optimally determine the model architecture for the voice conversion task. In the following, Berrak will talk about voice conversion, leveraging TTS systems, and leveraging ASR systems.
Hello everyone. Till here, we have studied beyond parallel data, disentanglement approaches, and having non-parallel data from paired speakers. Now we are still in the topic of beyond parallel data, but now we will be discussing leveraging TTS and leveraging ASR, which are really exciting subtopics of beyond parallel data. So the ideas to leverage TTS mechanism in voice conversion can be motivated in many different ways. If you look at it, TTS and voice conversion, TTS flow as given here, we have a text, an encoder, attention, and decoder mechanism. And some of the voice conversion methods can also follow this structure, right? We may have a source speech as input. We can have encoder, attention, and decoder. As you can see, these two follow similar encoder-decoder with attention architecture. And I would like to note that a TTS system is equipped with a quality attention mechanism here, and that is really needed for voice conversion, especially for duration modeling. And a TTS system is trained on a large speech database that offers a high-quality speech reconstruction mechanism given the linguistic content, because as you may all know, in voice conversion, we have limited training data. And if we use TTS model, which is trained on a large speech database, it can improve our voice conversion performance, which we will also study briefly today. So I would like to start with a paper that is published in 2019 InterSpeech. In this paper, there is this motivation that both TTS and voice conversion can be benefited from each other because both can be divided into two parts, that is an encoder and an acoustic decoder. And the authors are proposing to train TTS and voice conversion together to see if this method can improve the voice conversion performance. So it is mentioned that even though various successful methods have been proposed for TTS and voice conversion, most of the systems can achieve only one task. So to construct one model shared for both TTS and voice conversion is the aim of this paper. And you can see the overall architecture here. Today, we will not go into the details of each step that is provided here, but I want to highlight that we have an encoder and decoder model that supports multiple encoders. And this actually framework improves the performance of voice conversion compared with the model standalone. So let's look at, this encoder part first. Let's zoom into this. So as you can see here, this is the text encoder, and we have the character embeddings here. And given text characters as input, this model conducts end-to-end speech synthesis. And for the voice encoder, as you can see here, voice conversion encoder, we have the source male spectrogram as the input. And given the spectrogram, the model conducts sequence-to-sequence voice conversion. So this is just one way of training voice conversion and TTS together. And if you check this paper, you will observe that this module actually improves the voice conversion performance quite a lot compared to standalone sequence-to-sequence voice conversion framework. So another leveraging TTS idea comes from Kotatron, which is a really recent paper from this year's InterSpeech. So in this Kotatron paper, we have a transcription-guided speech encoder. And this speech encoder is actually based on multi-speaker TTS. And here, authors are encoding an arbitrary speaker's speech into speaker-independent linguistic features. And then we will be, using these features as an input to the decoder that can perform any to many voice conversion. So if you already know PPG-based voice conversion algorithms, you will understand that the idea behind Kotatron voice conversion is really similar to PPG-based voice conversion model, to having the speaker-independent linguistic features and then learning a mapping from these features through a decoder-based architecture. But if you are not very familiar with PPG-based voice conversion models, you don't need to worry about it, because later today I will be also talking about PPG-based voice conversions under leveraging ASR. So Kotatron voice conversion uses this TTS encoder that we have described to extract speaker-independent linguistic features. And then the decoder takes this attention-aligned speaker-independent linguistic features as the input and the target speaker identity as the condition to generate a target speaker's voice. As you can see, the idea here is similar to PPG-based voice conversion models, but here, rather than leveraging ASR, we are leveraging a multi-speaker TTS. And here, voice conversion actually leverages the attention mechanism or shared attention from TTS. So another idea to leverage TTS comes from TTS voice conversion transfer learning. Again, this paper is very recently published in 2020. So here the idea is that we first train a multi-speaker Tokatron 2 on a large database and then transfer the TTS knowledge to an encoder-decoder architecture for voice conversion. As you can see, and we have also we have also discussed this in the previous pages. We have the encoder structure, attention, and decoder from TTS. And we have this encoder here and decoder for voice conversion. So through this transfer learning, we can actually improve the voice conversion performance. And later, I will also show other papers that are using similar ideas to this. So I want to highlight that there are two assumptions behind this framework. The first one is that the context vector generated by TTS is speaker independent, and TTS decoder can work for voice conversion, because as you can see, it will be used for voice conversion here. So this is the main assumption behind this framework. And in the experiments, it is shown that this framework actually improves voice conversion a lot. So there is also another paper, pre-training TTS model for voice conversion. So in this paper, the motivation is that it is actually something that everyone knows. Sequence-to-sequence models are data hungry, right? This is something really well known. And sequence-to-sequence voice conversion model based on transformer architecture with TTS pre-training. This is what the authors are focusing in this paper. They are proposing a pre-training technique to transfer knowledge from learned TTS model, which will benefit from large-scale TTS corpora, because as I said previously, voice conversion suffers from the limited data problem, so having a TTS that is trained from large-scale corpora will for sure improve the voice conversion performance. And in these papers, authors are focusing on transferring knowledge from transformer-based TTS to a transformer-based voice conversion. This paper is recently published in InterSpeech 2020. So there are also many other interesting approaches. For example, from 2018, we have text supervision to improve sequence-to-sequence voice conversion. And last year in ASRU 2019, we have this Nautilus, a voice cloning system. And there is also a recently submitted paper in arXiv this year on this, and a transaction paper as well. And another idea is speaker adaptive TTS model for voice conversion, again from the same authors, Leong and Yamagishi in ASRU 2019. So there are really very interesting approaches that leverages TTS in voice conversion. We have other interesting approaches as well, but due to the interest of time, we will not study all of them. I hope that you, after this presentation, you can understand that this leveraging TTS in voice conversion is actually a very interesting research direction. So with the deep learning era, actually, there are lots of interaction between TTS and voice conversion algorithms. And by leveraging TTS, we hope that we can improve the training and runtime inference of voice conversion. And so I would like to highlight that even today, most of the techniques that I talked about usually require a large training corpus, even for voice conversion. So we believe that it deserves a future study as to how voice conversion can benefit from TTS systems without involving large training data. So we believe that this can be really an interesting future study. So let's briefly talk about leveraging ASR for voice conversion. So we know that most of the ASR systems are already trained with a large corpus, right? And they already describe well the phonetic systems in different ways. So here the question is how to leverage the latent representations in ASR for voice conversion. So one of the first papers that we would like to study today is phonetic posterograms for voice conversion. This idea was proposed by Li Fa-san and his colleagues from Hong Kong. So here, they are building a mapping function to convert phonetic posterograms to acoustic features. And the whole assumption is that these phonetic posterograms are speaker independent. So they are using an ASR system here during training of voice conversion. They have the target speech and they are using this ASR system to get the PPGs. And after that, they are training PPG to acoustic feature mapping here with BLSTM. And after they train these models, during runtime conversion, they have the source speech and they are using the same ASR and to get the PPGs here. And after that, they are directly taking the models that they train that can map the PPGs to the converted features. So they are mentioning that the PPGs are derived from a well-trained ASR system. So it can be considered speaker independent. This is the main assumption behind this framework. And because of this assumption, sometimes the voice quality may not be very good, because even though it is assumed that these PPGs are speaker independent, in real life, when we build these modules, we observe that they are not really very speaker independent. So a follow-up on this topic is by Shanghai Tian in Odyssey 2018, and there are also other papers following these two papers as well. And in this paper, Shanghai proposes an average model adaptation idea. So we first build a mapping function to convert PPGs to acoustic features, similar to Lifasan. But how we do it is slightly different. It is this training step 1, okay? So as you can see, Lifasan was using target speech. However, this paper uses multi-speaker speech and to get the PPGs and then to learn the mapping. So basically, you know, we have this mapping now, but this mapping doesn't only map from the PPGs of target to PPGs of spectral PPGs of target to spectral features of target, but instead it learns this mapping for all the speakers that we have in the data set. So after that, we have the stage 2 during training, which is the adaptation. So in this step, we actually use, Shanghai uses very small training data, like 20 utterances or something like that, to train this adaptation. And once we adapt our network to the target speech, then at runtime, when we have the source speaker like this, we can use the same ASR to get the PPGs and use the adapted train and adapted network to get the converted features. And this idea, the PPGs together with average model adaptation voice for voice conversion, improves the limited data voice conversion performance a lot, mainly because of this adaptation stage. And I want to highlight that this adaptation stage is the only stage where we use target data. So average modeling and PPGs for voice conversion became really popular in the recent years. So we have like a paper from Interspeech 2019 that learns from PPGs to waveform conversion with WaveNet directly. And some papers on emotional voice conversion, cross-lingual voice conversion, and monolingual voice conversion with limited data. So these are all recent papers, and there are also other interesting works as well on this particular topic. So when we leverage ASR, it was mostly on generating the PPGs and building voice conversion models around it. And in our published overview paper in IEEE ACM transactions, you can also see more details on other papers that are leveraging ASR and leveraging TTS as well. We hope that this can be just a short summary of leveraging ASR and leveraging TTS ideas behind voice conversion. So from here onwards, I will be talking about evaluation of voice conversion, which is again a really important topic of voice conversion. I will be describing objective evaluation for spectrum and prosody, subjective evaluation, which are the listening experiments, and Tsao will describe the neural approaches. So let's start with objective evaluation. If we are performing spectrum conversion, One of the most famous and widely used objective evaluation metric is malcapsular distortion, and it is used for many researchers around the world in the last more than 20 years. And I want to highlight that in malcapsular distortion, we are basically looking at the distortion between the original target spectrum and the converted one. So, and a lower malcapsular distortion indicates a better performance. And it is known by the community that malcapsular distortion actually is not always correlated with human perception. So when we are publishing papers, only providing MCD scores oftentimes is not good enough. That's why we also need to conduct listening experiments where we invite human listeners to listen and grade and judge our speech samples. So MCD is just one of the objective evaluation metric for spectrum conversion, and it is not the only one. The second widely used is log spectral distance, and similar to malcapsular distance, log spectral distance, again, a lower value indicates a better performance. And it is really similar to malcapsular distortion. Log spectral distance is not always correlated with human perception. So in voice conversion, we have this problem. Our objective evaluation metrics are generally not correlated with human perception. That's why we always need to perform listening experiments as well for fair evaluation of the voice conversion algorithms. So there are also other used, not very widely used, but used ideas for spectrum conversion that are discussed in our overview paper, but for the time of the interest of the time, we will be only, in this presentation talking about MCD and LSD. So for prosody conversion, if we are converting F0 or energy contour, you will observe that Pearson correlation coefficient, which is also denoted as PCC in the community, has been widely used to evaluate the conversion of F0, and a higher PCC value represents better F0 conversion performance. And same for energy contour. Another F0 and energy contour conversion evaluation metric is root mean square error, that is also denoted as RMSE. So similar to actually opposite to PCC, RMSE, if we have a lower value, it represents better conversion. Whereas for correlation, we need to have a higher value. So there are also generally accepted metrics for prosody transfer other than RMSE and PCC. The first one is F0 frame error, which is denoted as FFE. And this one reports the percentage of frames that either contain 20% pitch error or a voicing decision error. And the second generally accepted metric for prosody transfer is gross pitch error, which is also denoted as GPE. So this reports the percentage of voiced frames whose pitch values are more than 20% different from the reference. So these are the generally accepted metrics for F0 and prosody conversion. And as I previously mentioned, in voice conversion, we have this problem that objective evaluation metrics are really not, good enough to evaluate the performance of the voice conversion algorithms. So that's why we also need to conduct listening experiments. And if you read the recent papers or, papers from even 10 years, 20 years ago, you will observe that mean opinion score is really widely used. And basically in mean opinion score, we have human listeners, and these listeners rate the quality of the converted voice using a 5-point scale. Here, 5 means excellent quality, and 4 means good, 3 means fair, 2 means poor, and 1 means bad. So this mean opinion score has been widely used in many papers. And it is one of the evaluation metric that we almost all the time have in our publications to compare the baselines with the proposed approaches. So here, as you can see, we have the human listener listening and deciding the quality of a given speech sample. There are also some other evaluation methods that are similar to MOS. One of them is DMOS. And this is This looks at the degradation or differential MOS test, requiring listeners to rate the sample with respect to a reference. And we also have Mushra, and Mushra requires fewer participants than MOS to obtain statistically significant results. So these are, accepted evaluation methods for voice conversion as well. MOS is more popular, but you can also observe DMOS, and Mushra in many of the voice conversion papers. And we also have other evaluation techniques that require human listeners. And these are mostly for direct comparison of two speech samples, AB, ABX tests. So when we are using AB tests, basically we are giving two speech samples to the listeners, and we are asking them to indicate which one has more of a certain property. For example, in voice conversion, we may ask which one is better in terms of naturalness, or which one is better in terms of similarity. And this is the AB test. And if you are doing ABX test, in this, it is really similar to AB test, but we are giving two samples together with an extra reference. And listeners need to listen and judge if A or B is more like X in terms of naturalness and similarity, or it can be even in terms of emotional quality or emotional similarity. This is how AB and ABX test has been used in voice conversion. So that was all till neural evaluation metrics. With the deep learning era, we also have some basic evaluation metrics depending on deep learning methods, which will be discussed by you, Tsao.
Okay, thank you, Berrak. I'm going to take over for now. In the following few slides, I will explain the neural evaluation matrix. As introduced by Berrak, the neural evaluation matrix is about to build evaluation matrix based on neural network models. We think this research direction is quite interesting and important. The reason is, for normal subjective listening tests, the recruited subjects have to listen to the converted or synthesized speech generated by a machine, and then give scores of quality, intelligibility, or similarity. Of course, if we want to obtain an unbiased evaluation results, we should recruit many subjects to participate in the listening test. And each subject needs to conduct a large amount of listening tests. Of course, this is a very challenging task and may not always be practical. Therefore, our intention is to design some models that can serve as surrogates to the listening tests. To this end, we propose the MOSNet in Interspeech 2019. The MOSNet is a deep learning-based objective assessment for voice conversion. The MOSNet is formed by a combination of CNN and BLSTM. The input is synthesized or converted speech, and the output is subjective listening test scores. We use the materials from the Voice Conversion Challenge VCC 2018. In VCC 2018, it provides the paired speech and the corresponding listening test scores. With such speech signals and the scores, we can train a prediction model. Given the speech signal, the prediction model generates a predicted score. When we train the model, the objective is to minimize the predicted scores and the true speech quality scores. This is the objective function we used to train this prediction model, which consists of two parts. The first part is utterance level loss, and the second part is frame level loss. We will investigate the effectiveness of the combination of these two losses in the experiments. The prediction results are shown in these two scatter plots. For each of these scatter plots, the x-axis is the true MOS score, and the y-axis is the predicted MOS scores. If the predictions are perfect, we will have a perfect diagonal line scatter plot. From these two scatter plots, we noted that the predicted scores from the MOSNet is highly correlated with the ground truth MOS scores. In addition to the scatter plots, which can visually present the results, we adopted other quantitative measures to test the performance. The three measurements include LCC, the linear correlation coefficient, and SRCC, Spearman rank correlation coefficient, and MAC, mean square error. We intend to see the contribution of the frame and utterance-wise losses. From the results, we can note that the combination loss give higher LCC and SRCC scores, and also give lower MAC score. The results show that the combination of frame and utterance level losses achieve better performance than individual ones. If we have such a quality prediction model, we can determine the optimal voice conversion model architecture online. As I have reported earlier, we can use the MOSNet to determine the sparsity value in the MOE-VC system, so that the overall system can strike a good balance between the model complexity and the online computation efficiency and the quality of converted speech. The same idea can be used to predict speech intelligibility. In APSIPA this year, we will present an STOI-NET, which is a non-intrusive speech intelligibility prediction model. The model of STOI-NET shares almost the same model architecture to the MOSNet, while there is an additional attention layer. Given the speech input, the STOI-NET aims to generate the predicted STOI scores. We want the predicted STOI score as close as the ground truth STOI score. And we also use the frame level loss and the utterance level loss to form the objective function. We evaluated the performance of STOI-NET on a noise reduction task. The results are shown in this slide. From this slide, we first noted that CNN BOSTN outperforms BOSTN. The results confirm the effectiveness of a combination of CNN and BOSTN over the BOSTN alone. Next, we noted that CNN BOSTN plus attention mechanism outperforms CNN BOSTN. The results confirm the effectiveness of the attention mechanism to further improve the prediction accuracies. We also draw the scatter plots to compare CNN BOSTN and CNN BOSTN plus attention mechanism. The results in these two scatter plots show that with the attention mechanism, CNN BOSTN could achieve better performance. For the next part of this tutorial is about voice conversion challenges. I'm handing over the next part to Berrak.
Hello, everyone. After this evaluation techniques of voice conversion, now we will be briefly talking about voice conversion challenges. And after this part, we will study emotional voice conversion together, and we will also talk about a data set we recently released that allows conversion of emotion and speaker identity. So first, let's start with voice conversion challenges. In this part, we will be covering 3 topics: Voice Conversion Challenge VCC 2016, VCC 2018, and VCC 2020. So let's start with VCC 2016. This was the first shared task in voice conversion, and the task was to perform parallel data voice conversion in monolingual setup, which means that source and target speakers are speaking the same language, and we have data from both speakers, and this data is parallel. So as you can imagine, this is like one of the simplest ways to perform voice conversion. And in VCC 2016, 17 participants submitted their conversion results, and 200 native listeners of English joined the listening test. And what did we learn from VCC 2016? To start with, the best system uses GMM and waveform filtering. And we also understand that there is still a huge gap between target natural speech and the converted speech. And it remains an unsolved challenge to achieve good quality and speaker similarity at the same time. And this was, again, 4 years ago. So where we are right now in voice conversion is a little bit different than where we were in 2016, which we will be discussing in VCC 2020 part as well. So for the data set of this challenge and for the implementations of the baseline and also for the speech samples, you can basically, check the, check this website that we provide here. So you can find the data set, more details about the challenge, as well as the baseline implementation and some speech samples. So 2 years later, VCC 2016, we have VCC 2018. And this task is similar to VCC 2016 in some aspects, but it also has more work to do. So basically, we have 2 tasks in this challenge. And the first task is parallel data voice conversion, which is kind of similar to VCC 2016. And we also have non-parallel voice conversion in this challenge. So if you look at the parallel voice conversion part, it is really similar to that of VCC 2016. But now we have a smaller number of common utterances by source and target speakers, which means that it will be a more challenging task because the less data we have, the voice conversion task becomes more and more difficult. So this was the parallel VC part. For the non-parallel VC part, this is the first time to, have a challenge that attendees are building non-parallel voice conversion frameworks because VCC 2016 didn't have this at all. And basically, the same target speakers data in the parallel test are used as the target here, and the source speakers are 4 native speakers and different from those the parallel conversion test. So basically, 2018 voice conversion challenge covered both parallel and non-parallel voice conversion, but I want to highlight that this was still a monolingual setup, which means that source and target speakers speak the same languages. So what are the important aspects of this VCC 2018? The first one is to bridge the gap between automatic speaker verification ASV and voice conversion communities. And there was also a discussion on how to assess the spoofing performance of voice conversion systems on the basis of anti-spoofing scores. So these were the 2 important aspects of this challenge. But I want to highlight that this was the first time for attendees to build a non-parallel voice conversion task. So this was 2 years ago, and we have provided the link for you here. If you are interested more in the details, you can, just go and check this link to learn more about Voice Conversion Challenge 2018. So, and this year we had another Voice Conversion Challenge. And in this challenge, we had 2 tasks now, and this can be seen as a more intensive challenge because we had monolingual case and cross-lingual voice conversion. And this was the first time to build cross-lingual voice conversion in a voice conversion challenge. So the first task was parallel and non-parallel monolingual voice conversion. You can see this kind of similar to VCC 2016 and VCC 2018. And secondly, we have non-parallel cross-lingual voice conversion. And these cross-lingual voice conversion setups were from English to Finnish, English to German, and English to Mandarin. So, and there were baselines published. The first baseline was cycle VAE, and the second baseline was ASR plus TTS-based VC. So we have studied the traditional evaluation metrics together today in this tutorial, right? So in addition to those traditional evaluation metrics, this challenge also reports the speech recognition, speaker recognition, and anti-spoofing evaluation results on the converted speech. So this really makes the analysis of the results really interesting. If you are interested to, get the codes and the baselines and also these publications, please check this website that we provide here. So this is a table that briefly compares Voice Conversion Challenge VCC 2016, 2018, and 2019. So if you look at here, VCC 2016 was a monolingual challenge. And VCC 2018, again, was monolingual. On the other hand, VCC 2020 has monolingual and crosslingual cases. So if you look at the task, for VCC 2016, it was parallel, which is kind of simpler. And for VCC 2018, we had parallel and non-parallel setups. And for VCC 2020, we had parallel and non-parallel in monolingual and non-parallel in crosslingual cases. So in these challenges, we have different number of training set and test set. And you can see the number of speakers, and you can also see the number of testing data. This is just a very brief comparison of these 3 challenges. If you want to learn more about these challenges and the comparison of them, please check our overview paper because we have provided a more detailed discussion there. And also you can read their own papers on this voice conversion challenges, because every year when the challenge was organized, the organizers also published papers separately for each of these challenges. So please do read them and this overview paper to understand the differences between these challenges and the results of these challenges. So this was all for voice conversion challenges. I hope that it is more clear to you right now. And I hope that you can, briefly understand what was the aim of these challenges. It was really good for all the voice conversion teams around the world to come together, to the same platform and implement their frameworks with the same data to compare. It also gives a good start for the new students to understand the voice conversion field and to understand which sort of frameworks work better than others and in which sort of setups, basically. So from here onwards, I will be talking about an application of voice conversion, which is emotional voice conversion. Actually, the introduction of this part has been done by Haizhou, but now I will discuss a little bit more about emotional voice conversion. And before finalizing this presentation today, I will also show you a very recently released data set that allows you to perform not only voice conversion, but also emotional voice conversion. So let's start with emotional voice conversion first. Emotional voice conversion aims to convert one's voice from one emotion state to another while protecting the speaker identity and linguistic content. So as you can see here, we have a happy person, right? And this happy person is saying hello in a happy voice. And emotional voice conversion aims to convert the emotional state of this utterance to make it sad or to make it surprised or maybe angry or neutral. So this is basically the aim of emotional voice conversion. And emotional voice conversion is a more niche area compared to the traditional voice conversion. But in the recent 3-4 years, there have been some implementations that can successfully convert emotional states up to some level. So today I will just show 2-3 implementations of emotional voice conversion so that it is easier for everyone to understand how a framework can perform emotional voice conversion. And I also choose the frameworks that have their codes and speech samples publicly available so that it is easier for all the listeners today to basically replicate these frameworks. So the first framework is from our student, Jo Kun, in InterSpeech 2020. And the title of the paper is kind of long, but it starts with converting anyone's emotion. So basically, this is an emotional voice conversion framework. And it doesn't matter who the source speaker is, whoever comes, this framework can perform emotional voice conversion, which means that the speaker can be me, Haizhou, or you. This framework can perform emotional voice conversion to all of us. And this framework only trained under neutral to angry setup in this paper, but it can be easily implemented for other conversion setup as well. As you can see, this is a VAW GAN-based framework. And for simplicity, we use world vocoder as the vocoder for analysis and synthesis. But WaveNet or WaveRNN can be implemented in this setup as well. So we have an emotional speech and we have an emotional ID here. And we use world vocoder to get the spectral and F0, spectral features and F0. And we have 2 VAW GANs here, one for spectral features and one for prosody features. Interestingly, some preliminary experiments also reported that training separately for spectrum and prosody improves the performance rather than training them together. So by following that motivation, we propose to train spectral and prosody conversion separately in this paper so that we can achieve better emotional conversion performance. And we have encoder, we have a generator, and we have a discriminator, as you can see, for both spectrum and prosody. And we also have emotional ID. And for this particular setup, we have the emotional ID of neutral and angry. So after training this with many speakers' data, you can actually learn an encoder generator discriminator, which means like a VAW GAN architecture setup for spectrum and prosody conversion. We have provided all the codes in this GitHub page, as well as how to run them. So feel free to, just check this website to understand how you can just repeat these experiments and get emotional voice conversion results. And I want to highlight that at this time, when we wanted to build such a network, we need to have a lot of speakers, right, with different emotions. And it was challenging for us to find such data, which motivated us to build an emotional speech corpus and make publicly available, which will be the focus of the next slides as well. But so basically, like similar to voice conversion or TTS, when you want to build a large network that can convert many speakers' voice or maybe an average modeling network, we require to have more speakers' data, and this was missing in emotional voice conversion area. So let's look at another implementation here. This is a seen and unseen emotional style transfer, a paper that is submitted to ICAST, but it is available in arXiv, And the codes are also publicly available as well as the speech samples. So if you just follow these, the steps that are provided in this GitHub page, you can get the same results that we reported in the paper. So as you can see, this framework is a little bit more sophisticated because in the previous one, when we were representing emotion ID, it was a one-hot vector. But now, rather than using a one-hot vector, we train the speech emotion recognition model, and we get an intermediate latent representation that we call deep emotional feature as an input to the VAW GAN, especially to the decoder, together with the encoder output emotion independent latent representation. So this, two features and F0 coming together, emotion independent latent representation, deep emotional features and F0, we can actually learn a better representation for emotional voice conversion. It is really easy to repeat this experiment. You can just check this GitHub page provided here. So these are, just basic ways to perform voice conversion and to perform emotional voice conversion, and the accuracy, the performance that we get from these frameworks are really good. So there are also other emotional voice conversion frameworks that are actually submitted and published recently. The first one is Zhao Luo in 2019 in IEEE ACM Transactions. This paper uses wavelet transform for F0 features and emotional voice conversion using dual supervised adversarial networks. And there are also some other interesting works, for example, from InterSpeech 2019 and also from ICAST 2019. Again, ICAST, StarGAN for emotional speech conversion, and multi-speaker emotion conversion via latent variable regularization and a change encoder-decoder prediction. So there was also a session in InterSpeech that purely focuses on emotion and emotional voice conversion this year. So I would like to highlight that emotional voice conversion was a niche area, but now it is becoming more and more popular in the recent years, especially in 2019 and 2020. But in all of these papers, it was clearly mentioned that having a proper data set with emotion labels, clean data set with parallel utterances from many speakers, hopefully monolingual and cross-lingual setup is really important because all of these frameworks suffer from the data sparsity up to some level. And with that motivation, we will be showing you a new data set here today. But before that data set, I would like to list all of the open source emotional database, all of the, actually not open source, like these, some of them are open source here only, but basically I would like to show all of the data sets that have emotional speech samples inside. And the challenge is that lack of open source emotional database. We have listed 9 data sets here. As you can see, the first 4 data sets have limited diversity of sentences. If you look at the first data set, it only has 2 different English sentences read by 24 actors in 8 emotions. So only 2 different English sentences. And for the second one, it is 12 English sentences by 91 actors and 6 emotions. The third one is Berlin emotional data set. It is by German sentences, but only 10 German sentences spoken by 10 people in 7 emotions. And the saved database is 15 different English sentences by 4 male speakers in 7 emotions. So if you look at the number of utterances that we have in these 4 data sets, just 2 in the first one, 12 in the second one, 10 in the third one, and 15 for the fourth one. These are really extremely limited for voice conversion frameworks to be trained, right? And I mean, it is really very challenging to train a voice conversion framework with only 2 different English sentences. And I also want to highlight that their emotion labels are not consistent. For example, the first data set has 8 emotions, the second one 6, and the third and fourth have 7. So basically, you cannot just combine them to have a bigger data set. Moreover, the third one is in German, not even in English. So this makes things even more complicated to combine these data sets. The fifth and the sixth data set have larger data, like 9 hours of audio visual from 12 actors and 12 hours of audio visual data from 10 speakers. But I want to highlight that these two databases contains overlapping speech and external noise. So it is really not very suitable for speech synthesis nor voice conversion. That's why, unfortunately, these data sets are also not very flexible for emotional voice conversion use. And the seventh one is EmoVDB database. We have here like 300 different English utterances recorded by 4 speakers. This data set only have 4 speakers, which is really not good enough to build average modeling sort of ideas or to build multi-speaker emotional voice conversion frameworks. Previously, we have used this dataset in our publications, but once we want to build bigger frameworks that can work for multi-speakers, then this dataset is also not good enough. And this dataset also contains non-verbal expressions, limited diversity of speakers. And as you can see, one cannot easily perform voice conversion with these datasets as well. And for the last two, CMU Arctic Speech Database, which is a famous database in voice conversion as well, and AMUS database, which means all amused utterances. These two datasets only contains one single emotion. So performing emotional voice conversion requires you to have more emotional states from many speakers. And with this 8 and 9 databases, it is really not possible as they only have one emotional state. So as you can see, even though it seems like there are many emotional databases out there, it is really not practical to use any of these frameworks directly for voice conversion and for emotional voice conversion. So this was a challenge in emotional voice conversion. And very recently, in this ICAST, we submitted a new emotional speech dataset, and you can also find this paper available in arXiv right now. We basically released a new multilingual and multi-speaker parallel emotional speech dataset. I want to highlight that we have multilingual setup, we have English utterances, and we have Mandarin utterances, which is a dialect of Chinese. And we have multi-speaker parallel emotional speech dataset here. So this dataset can be used for speech synthesis and voice conversion tasks. It can be used for monolingual voice conversion. It can be used for cross-lingual voice conversion. And it can also be used for emotional voice conversion for monolingual and cross-lingual setup. And I mentioned that we have parallel utterances, and from each 10 native English and 10 Mandarin speakers, we have 350 parallel utterances. And for each language, the dataset consists of 5 male and 5 female speakers with 5 emotions. This is consistent throughout the dataset. We have 5 male and 5 female English native speakers and 5 male and 5 female Mandarin native speakers. And all these speakers are speaking 350 utterances 5 times, and each time they have a different emotion. And our emotions are the widely used emotional labels of emotional voice conversion that are neutral, happy, sad, angry, and surprised. So if you just use the neutral, you can directly build traditional voice conversion frameworks. And if you also use the other labels, then you can also as well learn emotional voice conversion models. And this dataset is available online for academic use, and you can directly download it from HLT Singapore GitHub page. And this is the paper. If you're interested to know more about the details of this dataset, it is right now on arXiv, and it is also submitted to ICANS, as stated also in the arXiv website. And we are also writing a technical report on this dataset that shows that this dataset allows everyone to perform voice conversion, which can be monolingual and crosslingual, as well as emotional voice conversion in monolingual and crosslingual setups. So to sum up, in this presentation, Haizhou provided an introduction to voice conversion, and he also, talked about the history of speech synthesis and voice conversion. Then, together with you, Tsao and I, we have studied parallel data for voice conversion, beyond parallel data for voice conversion. And beyond parallel data for voice conversion had lots of topics inside, right? We had non-parallel data of paired speakers. We had disentanglement, leveraging TTS, and leveraging ASR. And after that, we have studied evaluation of voice conversion together. In evaluation of voice conversion, we had 3 subtopics that are objective evaluation, subjective evaluation, and neural evaluation metrics that you saw had a short discussion about. And then we have studied the voice conversion challenges briefly. We had 3 topics here, VCC 2016 that has monolingual parallel data set, and VCC 2018 that has a monolingual setup again, but now parallel and non-parallel tasks. And the recent VCC 2020 where participants need to build crosslingual and monolingual voice conversion frameworks, both in parallel and non-parallel setups. And after that, I have provided 3 emotional voice conversion frameworks that are published very recently by our students, and their codes are also available publicly in GitHub. So feel free to check those links and just repeat the experiments. You can use those as a baseline in your own papers as well. And after that, we had like a short discussion about the challenges of emotional voice conversion. And one of the important challenges is to have a large data set that is publicly available. And I listed 9 data sets that can be used for voice conversion and emotional speech voice conversion. And I also highlighted that all of those data sets have challenges and that limits the research that can be done in emotional voice conversion. And with this motivation, we propose a new data set for voice conversion and emotional voice conversion that has 350 utterances from 10 native English speakers and 10 native Mandarin speakers that can be used for monolingual and crosslingual setup. So thank you very much for attending our session today. And we would like to thank our team members at National University of Singapore, Singapore University of Technology and Design, and Academia Sinica. And we also would like to thank our PhD student, Joe Kun, for helping us to make his codes publicly available for academic use. So thank you very much.